Welcome, students, to the lecture on stature estimation, or what you may also think of as living height. Living height and stature are oftentimes included in missing persons reports, and so it provides an extra variable and parameter that we can use to make a positive identification. Right, we are in the biological profile. We've done 1, 2, and 3, and now we're working on 4. And then I will shortly post the lecture on pathology, which includes any diseases, but mostly things like traumatic injuries to the skeleton. Living stature is an important component because it is reported on missing persons reports. You'll also notice that when you leave a Circle K or a gas station, your convenience store, you will notice even as you walk outside towards the door, there will be height measurements, right? 4, 5, 6 feet on the side. And that's so if somebody can look at the door, like an employee or another witness, and watch them walk out the door, they will be close enough to that measure, that gauge, so that they can actually determine, how tall that person was. And this is a variable oftentimes used in, criminal investigations. So it's important to try and estimate. Stature or living height is a typical part of the biological profile, again, because it's oftentimes reported, a variable that's oftentimes included in, these types of correspondence. And it's oftentimes done after you find out age, sex, and ancestry. And this is because we know that there is variation in height based on binary sexes. We also know that as you age, your vertebrae tend to, they tend to squeeze or press down a little bit more because of the longevity and the atmospheric weight of gravity. So over time, you get shorter just because of that atmospheric pressure on you for so long. And then we also have things like osteoporosis, which is an increased porosity of bone, which can also make your bones, weaker and prone to fracture. We also know that people of different ancestral backgrounds, there are specific variations in terms of leg length as well as torso length that we need to account for when we estimate stature. So you need other parts of the biological profile, is what I'm saying, so that you can actually get at stature estimation, for instance. And we have a pretty good idea that the lengths of various bones are correlated with stature. Matter of fact, one of the foremost bones that has one of the best correlations with living height or stature is the femur or the tibia, or a combination of both. Most studies that I am familiar with, usually the femur and or the tibia, or a combination of both measurements, are between 80 to 90% or more accurate. And it makes a lot of sense. Your leg length is a major contributor to height, and then bones of the arm are not as accurate. Maybe they're 60% or less. Although if you only had bones of the arm to use, then that might be the only way to get at a stature estimation. What we're going to cover here are, some basics of stature reconstruction and historical background. Talk about different types of methods that are used, both with a complete skeleton if it's available, or with long bones. And then, forensic anthropologists also used an experiment with other skeletal elements so that, that they're able to use other bones if there is a correlation, a positive correlation with, a bone measurement and height. And then we'll talk about some additional adjustments that oftentimes need to be made. The basics of stature reconstruction hold that there is a positive linear relationship with living stature and the lengths and heights of bones, including the vertebral column, maybe even the pelvis. And most commonly, limb bones are used, but people have also looked at some of the length of foot bones. So we see a positive linear relationship with limb bones and other bones. What that means is, for instance, we can take the femur. The longer the femur, the taller the person, right? That's a positive linear relationship. The taller the person, the longer the femur. So, it's closer to a 1-to-1 correlation. Thomas Dwight, remember, one of the founding fathers of U.S. forensic anthropology, he was one of the first people to document these relationships. And since then, we have a widespread industry of forensic anthropologists and other like-minded researchers that measure and try to estimate living stature. It was done on a number of collections that were accumulating in the early 20th century, and people have modern donated collections that we can also use to create new formulae to estimate living stature. We also know that people are taller than ever before. Matter of fact, in the last 50 or so years, people are much taller than individuals from, let's say the 1950s and 1960s. Goodness, my grandfather was a center at Michigan State football, and he was 5'7", and there's no way he would be able to survive in that position today at that height and presumably his weight, because we know those individuals now are, 6'5" and 300 pounds. That probably has to do with increased access to calories, as well as workout regimens that allow us to put on more muscle mass. Before we get into the nitty-gritty of stature estimation, let's go over some of the common and sometimes troubling issues. So these are some of the challenges that we face when we conduct measurements, as well as issues in terms of accuracy and precision. One is inter-observer error. So there's two different types of error generally. There's always the error of the actual machine that you're using, or the calipers, or the device. That could be faulty, or it's not maintenance, like you don't have a fresh battery if it's a digital caliper, for instance. And so you can have error that's innate with the machinery. You can have intra-observer error. That's you measuring over time. Do you take the same consistent measurements over time, or is there variation? This may have to do with some of the points on the bone you're using. Is there some variation there? And then there's inter-observer error, and that's measurements between practitioners. So that's me taking a measurement and you taking a measurement, and what's the difference? What's the variation between our measurements? And we can quantify this. Researchers do all the time. I've measured tens of thousands of teeth several times, and I can figure out what my error is between those measurements of taking the same measurement. Some teeth that I measured 3 times to see how close I was. Generally, if you're within a few percent of, this is intra-observer error as well as intra-observer error, then that's pretty good in terms of the standard-wide industry. There's also variation in terms of ancestral background, age, environment, time of day, even can affect, a measurement of, and this is typically a living person. So stature varies by ancestry. We know this. And this means that there are different ratios from trunk length or torso length in comparison to the limb length. For instance, people with African or African American ancestry typically have longer trunks compared to individuals from other ancestral groups. So this is something that needs to be taken into account. That would also mean that there's a greater contribution of the trunk than the leg length. And this is why you need to figure out or make a determination of ancestry before you actually use a stature equation based on, for instance, maybe like a long bone. We have separate equations for, all ancestral groups that have been studied. We also know that the environment plays a role in living height, or the potential to reach, genetic potential to reach living height in terms of like a maximum height, we would think. So height is actually a number of components. So height is a phenotype, meaning it's something we can record and we see, right? We talked about phenotypes from genotypes, right? Genes that make something we see. That was discussed in the ancestry segment, the lecture just, 2 lectures just before. So the phenotype of your height equals probably 150 to 180 loci or points on genes. So we know from, a major study that was conducted even in the last 5-10 years that, we're talking about hundreds of genes that contribute to your living height, right? And of course, your maximum height doesn't occur until after you've gone through that delayed maturation or growth spurt, later growth spurt, which will happen a little younger for females, but with males, it happens later teens. So genes plus the environment as well as age, right? We've also discussed that too, make up your total height. If you don't get enough nutrients, vitamins and minerals when you're a child, when you're growing, then your growth will be stunted and you won't reach your genetic potential for height. So the environment plays a role in terms of height and how it manifests. We also know that age, as you age, after you've reached maximum height, the bones become more brittle and they're prone to fracture and they begin to compress because of atmospheric pressure for so long, gravity being on this earth. You will get a little shorter, you will shrink. We also know that if we measure your height after you wake up in the morning, you are taller than you are in the afternoon. We know that you're taller after you take a shower or a bath than before. And this is because, one, when you're sleeping, usually your muscles are relaxed and you're not tense. And this will, display a taller height measurement. We also know that when people are stressed, right, when there's lots of stress, that people tend to kind of tense up and will be shorter. We also see that after you take a shower or a bath, this relaxes a lot of your muscles and tissues and usually relieves stress or relaxes stress, and you will come out measuring taller. There's also bias, in not just in error in measuring, but how it's actually reported versus how it's, physically measured. A lot of times we get heights from, missing person reports, from driver's licenses, as well as, sometimes we'll get them from medical records, but oftentimes it's from, say, driver's licenses. And we have a steady trend that males tend to overestimate how tall they are on written records. So when you have a missing persons report and we get their information, from driver's license, and it goes out, and then we find, a decedent, and we're trying to get a positive identification, and our estimate is shorter than the missing persons report, right? Are we going to be confident to say that this is indeed that person, or there's a discrepancy with the height, and that might not coincide? So you have, usually have measured during life stature. You have cadaver measurements, how tall the person is, with the fleshy bits on after they have passed. Or are you getting the stature estimate and using reported stature to maybe calibrate that? So you can see that there are some problems there. And another component that I've alluded to is secular change. Populations over time evolve and change, and we record it, that we observe it. We're observing that variation. And some of the early 20th century collections that accumulated, like the Terry and the Ham and Todd, they're not very accurate anymore for use in modern people, because they lived and died, goodness, you're talking about, almost a century ago. For some individuals, 50, 70 years ago for most. We know that because of greater access to calories, that people are taller than ever before. And this is something that has only happened since the 1950s and 60s. And so using formula that was created using the Terry and Ham and Todd, because remember, these are people that are, that were war dead, people that were accumulated in medical collections, and we did have their reported stature on documents and driver's licenses. And we were able to create formula with, with long bones. But we know that those people are much shorter than people are today, and the formula are not accurate, not useful. One of the most accurate methods that we've discovered is known as the Fouillé method. He was a Frenchman, and I think this was developed even near the end of the 19th century. So it's a method that's over 100 years old, but it's still effective, and it makes a lot of sense. So if you have, all the skeletal elements at your disposal from, a crime scene, you can actually put the bones in their, natural articulation state. And then you can measure each one of these components, add the heights together, and that would equal how tall someone is. So typically what you do is you measure the height of the cranium, you measure the height of all of the vertebral bodies, minus the atlas, because that's kind of tucked, underneath, as well as it, doesn't have a vertebral body. And you also measure the first segment of the sacrum, you can include the height of the pelvis, and then you measure the length of the femur and the tibia, as well as the height of the ankle. Typically you take the calcaneus and talus and you articulate them together and you measure that height, right? Add all those heights together, you got somebody's total height. The only thing that's missing is probably a little bit of soft tissue that is, on the inferior part of your calcaneus, right? We have some fat pads that we use that give us a little bit of cushion when we walk and we step in, and a lot of that is on the heel. So that measurement could be, negligible and might only be, a few inches or centimeters. There are a number of problems with the Foley method. I mean, it's very accurate. It makes a lot of sense from, a practical standpoint. But look at all the elements you need. You need an intact crania. You need 23 vertebrae, sacrum, legs, bones, and 2 of the largest tarsal bones. What if the full skeleton is not recovered from a crime scene? And maybe it doesn't exist. Maybe other components were discarded and they will never be recovered. Well, how do you actually do this? Well, one way around this is some researchers have found ways to estimate little bits and components, like if you're missing a vertebrae, some vertebrae or vertebra here or there, then people have come up with equations to kind of supplement and fix that. We also know that there's soft tissue, like I mentioned the slide before, like in the heel, but there are also intervertebral discs that provide a little bit of space between your vertebrae. If you're just measuring the heights of the vertebrae, you're not actually including the intervertebral discs that will actually contribute to living stature, living height. We also know, because of the aging process, which is senescence and osteoporosis, as that skeletal elements begin to shrink. And you'll notice that the vertebral bodies begin to shrink in anterior view because of weight, right? And people will sometimes have, kind of a hunchback or a kyphosis. And that, contributes to height. And, that those numbers can change. People can report a change in stature and driver's licenses, as well as think about trying to measure the height of a vertebral body that has shrunk. Now, there are some ways, individuals has come up with other correction factors for age, and more people are thinking about trying to create a model that includes age into the actual estimation equation. And then we have one of the most popular methods is with lung bones, because we know that there is a positive linear relationship correlated with stature. That is, the longer the limb, or the longer, in this case, let's say the leg bone, because they're the most accurate, the taller the person is. Now, the longer their arm is that, taller the person, the longer the arm. For the most part, yes. But again, bones of the arm aren't as accurate as bones of the leg, because bones of the leg contribute more to, adult height than the arms do. But we know that there are limb proportions. People are proportionate legs to arms. So that does allow us to get at a stature estimation as well. We have Mildred Trotter to thank. Of course, Dwight was thinking about this and discussing it, but it was Mildred Trotter that did all the work on the Terry collection. And she actually created all of the formulae in the 1950s. And some people still use it, but, you probably can only use it on individuals who are elderly now, because it's not very accurate for modern populations because of secular change and selection for humans getting taller. There are additional skeletal elements that correlate with stature. We know that maybe the metatarsals, the metacarpals, and the vertebral column, right? We have tons of forensic anthropologists that, may measure any bone and then try to see if there is any correlation with living stature or height. And this would be effective. And what if you only found a metacarpal or a metatarsal at a crime scene? Then you would probably try to use this. Yeah, we think that we can even get a sex determination out of bones that this small, that there is some slight sexual dimorphism that we can detect even in the smallest bones, even bones of the ear, which is remarkable. So, it makes sense that forensic anthropologists would just find any bone they could that has a positive correlation with height and very effective in terms of that correlation coefficient, 80, 90%, then it can be used. And this opens avenues for all sorts of research. I have colleagues that have spent careers just, looking at one bone and trying to figure out whether you can determine, stature or even sex from one single bone, because you may only find that one single bone at a crime scene. Let's talk about some adjustments. We have a number of adjustments that have been made based on research and observations. One, of course, is that after 60 years of age, you begin to shrink or shorten a few inches. And this is because of atmospheric pressure and gravity. And usually your vertebral column begins to compress. The actual bones compress. This is because of the bones become more brittle and osteoporosis. And females, are more prone to osteoporosis because of hormonal changes after 60 years of age. And this reduces the length and the heights of a number of different bones that you would measure. Reported statures on driver's licenses, particularly for males, are usually greater than the stature we measure at a medical examiner's office or doctor's office, or even estimations that we get from just measuring bones. So that's something we also need to take into account. If we have a missing persons report and driver's license stature, we may try to find a medical record from a doctor's office that they actually measured it, and then compare that to the measurements that we get from the skeleton. So anytime we get a missing persons report and we're sifting through them, trying to find a positive identification based on the biological profile that we, generated from the skeleton, right? Comparing the data to missing persons to try to get a positive ID, we will then ask or find out, where did these numbers come from? If they say driver's license and they're male, we may actually try to get medical records. Medical records of living measured height are usually the most accurate by comparison.